Hi everyone. In this video I'm going to walk you through various variable selection procedures in R using the OLS-RR package. Before we get started, let me note that you can go to this link right here to obtain a copy of the data, which is saved in an R data file. I'll make that available as a link underneath the video description, and the data are contained in a data frame called regdata. Next, this text file that I have open, I will also make available as a link underneath the video description so that you can download it and follow along with the commands that I'm using. Also, the package information for OLS-RR can be found here. There's actually more in it than just variable selection procedures, but again, that's mainly what we're going to be focusing on in this particular video. If you haven't already done so, you'll need to install the package using the install.packages function. Inside our parentheses and quotation marks, we have the name of the package, OLS-RR. Once it's installed, you don't have to worry about reinstalling it, but you do need to use the library function to call it up. So we type in library, inside parentheses, the name OLS-RR. So with respect to the variable selection procedures, you have available forward regression, backward regression, and the more conventional stepwise regression. There's also all possible subsets regression. All of those are available through this particular package. When using forward regression, backward regression, or stepwise regression, there are actually two approaches for deciding on which predictors are going to be included or excluded from a model. One approach is the use of p-values, and another approach is the use of the Akaike's information criterion. So we'll start off with forward regression using p-values, and so we're basically laying out the regression model and specifying it the same way you would do any model in R. So you'll notice that I'm using the LM function, and inside the parenthesis we have the model specification. So the predictors of basically our model includes a dependent variable, which is achievement, so that's this variable right here, followed by a tilde sign, and then we follow it up with the names of the predictor variables that we see within our data frame. So we have mastery goals, interest, anxiety, and performance goals, and gender identification. All of those predictors are separated by plus signs. You'll notice that we have a comma, then followed up with data argument set equal to regdata, which is the name of our data frame. And we are saving our model information to an object that we're calling model. So you can see I've got a model followed by an arrow, which is just basically a less than sign followed by a hyphen, and then our specification right here. So once we've done that, then we can run our forward regression using one of the functions associated with the package. So this is the function right here. It's called OLS_step_forward_p. So it's quite a mouthful, but that's what it is. And inside the parenthesis, we have our model information that we specified up here. So the name model is going to appear right here. We have a comma and then p enter, and I'm setting that equal to 0.05. So in the context of forward regression, the process essentially begins by selecting the largest significant predictor with respect to contribution to the variation, to explaining the variation in the dependent variable. Then the next largest predictor that's statistically significant is selected, and so forth until a point at which no other significant predictors can be added to the model. So that's the p-enter. That's our threshold for entering significant predictors. You can see that we're also saving all of this information to an object that we're going to call fwd_fit.p, and this is just an arbitrary name, but this is just to kind of help me keep track of things as I'm going through all these different models. Then following down here, if I retype that name, then that's actually going to give me a short summary of the models at each step. So what I'm going to do is copy all of this and paste it into R and run the analysis. And so we'll kind of go up to the top here, and you can see we have our model information. There's model using the LM function. There's our data equals regdata, everything that we've talked about before. And then you can see that now we're fitting the model and saving information to that fwd_fit.p object. You can see below we have forward selection method with the candidate terms. These are the predictors that are candidates for entry. Then the variables that are entered are given next. So there's mastery goals, interest, and performance goals. You can see no other variables were added. So we have next the final model output with the multiple correlation here, the R-square value, the adjusted R-square, and so forth. We have our ANOVA summary table for that final model containing our 3 predictors. And then we have our parameter estimates table here, which gives us our intercept and the slopes for each of our predictors and significance tests. By typing in the fwd fit.p object name, you can see that we now have basically a description of the variables as they're selected at each step. So you can see at step 1, we have a model with just mastery goals entered, and there's the R-square value for that. At step 2, we add interest to the model. So now that model is going to include both mastery goals and interest. There's the R-square. And then the third model will add performance goals. So that model is going to contain all 3 predictors, and there's the R-square for that model. Now let's look at using the AIC. So this specification, we're just going to leave that as is. And in this case, we're just going to use the OLS_step_forward_AIC function. So in this case, we're going to save our information to an object that's called fwd_fit.aic. And you'll notice that following our function, I only have the name of our the object containing our model information. There's no p-enter to be included at this with this particular demonstration. So what we'll do is we will go ahead and I'll just kind of re-highlight all of this and paste it in, copy and paste it in. And you can see that you've got the forward selection method, candidate terms, and then the variables that were entered are mastery goals, interest, and performance goals. It says no more variables are to be added right here. If we want a summary of the models for each step, we can just we'll just copy this and paste it in. But again, that's our object is fwd_fit.aic. And so I'll actually, let me just kind of go down here. And so now you can see our selection summary. And so the selection of the predictors in the order that they are appearing are based on the AIC. So there's mastery goals, interest, and then performance goals right here. If we want to generate a plot to sort of look at the relative contributions of the predictors, we can use the plot function. We can just type in plot and then the name fwd fit.aic right here and hit enter. And so now you can see there's our plot. So mastery goals is contributing most of the model, followed by interest, and then followed by performance goals. And then one other thing, if you want to look at the intervening steps or the intermediate steps, we can rerun the analysis as we had before, but following model and a comma here, we can type in details, set that equal to true. So let's just kind of take a quick look at it. So we'll run the analysis here, and so now you get, you can see right here that we have step 1 that's given right here, and then essentially step 2 that's given right here, and then step 3 that is given right here. So now let's run a backward regression using p-values. So again, our model information is exactly the same as we had before, but in this case, we're going to use the OLS_step_backward_p function. And in this case, we're going to be talking about identifying variables that are essentially non-significant contributors to the model. So with backward regression, you start off with a full model, and then you select predictors that really add the least incremental predictive power to the model. And so you're essentially removing predictors, and if the R-squared change after removing a predictor is non-significant, then the reduced model is preferred relative to the full model. So our threshold we're going to use is PREM equals 0.05, and that's basically the p-value for removal. So we're going to save our information to a fit object that's going to be called bwd fit.p. So, and then we're also going to get the summary information for each step by typing this in again. So let's go ahead I don't really need to rerun the model. I've already done that. So I can just copy this and paste it in right here so that we can take a look. So up here, you can see there's our command right there. So it's backward elimination method. Candidate terms, it's got everything that we had before. Variables removed include anxiety and gender ID. And so then you have the final model output that's given right here. So there's the R-squared value, adjusted R-squared, and so forth. There's our ANOVA summary table down here, and then the parameter estimate. So it's basically giving us pretty much the same results that what we had before with the forward regression in terms of which predictors are entered, are included in that final model. By typing in bwdfit.p right here, you can see we have the elimination summary. So the first variable that was eliminated was anxiety, followed by gender ID right here. Okay, so in the interest of time, I'm not going to demonstrate this using the AIC, but the commands are in the text file that you can download. And so you can see right here that instead of using P at the end of the function, it's AIC that's given right there. So let's look at a standard stepwise regression using p-values. So you can see, again, there's our general model specification. So next, you can see we have OLS underscore step underscore both underscore P. So in this case, we're going to include a P entry threshold and a P removal threshold. So it's basically sort of a combination of both forward and backward regression. And in this case right here, we're going to save our stepwise regression results to bothfit.p. And this will give us our sort of our steps, our summary of the steps involved. So let's go ahead and run the analysis. We'll just copy this and paste it in again. And so there you go. So up here, you can see that we have stepwise selection method. Again, the candidate terms, variables entered or removed. And you can see that mastery, interest, and performance goals were in the final model. So you have the final model output again, the model summary as before, the ANOVA table, and parameter estimates that are given right here. And you can see the stepwise selection summary that's given right here after we've typed in the name of our object. And you can see step one, it's got mastery. It basically added a variable. Interests, we have an addition as well, and then we have performance goals, which was an addition. So it basically functioned the same way as the forward regression. Just kind of note that the reason why stepwise might be considered is, when you're running forward regression and you're adding in predictors, predictors are added in at later steps, or earlier steps could become non-significant at later steps. So basically, even if it becomes non-significant at later steps, then it still remains in the model because it was initially selected using that forward selection procedure. So the stepwise selection is basically going to try to eliminate those predictors that were significant previously but become non-significant at later steps. Okay, so another option available for selecting predictor variables is all possible subsets regression. So in the package, you have another function which it says OLS underscore step underscore all and then underscore possible. So in this case right here, we have the model information as before. And you can see right here that I'm essentially going to create an object that's going to be called mod compare. And then if I want to take a look at it, I can basically type that in. And then I will say that the information is saved in a tibble, and it's a little bit tricky to get all the model information that you might want to look at. So I'm going to actually use the function as.dataframe, and inside the parenthesis, the name of my object that contains all of the model information, which is mod compare. So just to kind of show you what I'm talking about, we'll rerun it and then generate the OLS, use the OLS underscore step underscore all underscore possible function. So I'm going to copy this and paste it in and hit enter. And we'll type in mod compare. And so you can see that we have, as I said before, a tibble. And you'll see that we have the first 10 models. We have an index for each of the individual models. And then right here, N is referring to the number of predictors, and then you see predictors that are included. So you can see that we have essentially 5 separate one predictor models. So one model has mastery only, one model has interest only, another has performance goals only, another with interest, anxiety, and then another with gender ID. Then we have all possible 2 predictor models, which include mastery and interest, mastery and performance goals, mastery and gender ID, mastery and anxiety, and so forth. And you can see that it kind of extends 20 more rows. 21 more rows. So in terms of fit measures for the different models, we have the adjusted R-square that's given right here, and then Mallow's C, which is given right here. And so these can be useful for comparing models and identifying models that contain essentially what might be considered as having the best subsets of variables. Now, the downside of the tibble is that we're kind of stuck with this piece of information right here. So I want to look a little bit more in depth at the different models. So I'm going to use the function that I was referring to before. So we're going to say as.data.frame, and then inside parenthesis mod compare. And so now you can see that we have all of the different models. So basically this is the model index. So we have basically models 1 through 31 down here. N is referring to the number of predictors. So you can see we have all possible 1 predictor models, 2 predictor models, 3 predictor models, and 4 predictor and 5 predictor models. So that you can obviously see we had 5 predictors, so there's only 1 of those models. And so you can look at various indices in order to sort of make a judgment as to which model demonstrates, or which model or set of models has the better fit to the data. Now, if you want to be able to sort of visualize the models to compare them, what we can do is we can use the plot function. So I'll type in plot, and inside parenthesis mod compare, and hit enter there. And so now you can see that we have various indices. Basically what you can see is along the x-axis right here, these are the number of predictors. Along the y-axis is the index of fit. So like this is R-square, this is Mallow's C right here, this is Akaike's information criterion, adjusted R-square that's given right here, there's Schwartz-Bayesian information criterion, and so forth. So the triangles that you see in each of these is reflecting essentially the best fitting model of a given number of predictors. So you can see that these are the 1 predictor models, the 2 predictor models, 3 predictor models, 4 and 5 predictor models. So you can see out of those, which model seems to kind of best fit the data. So with the CP measure, Mallow's C right here, basically a lower value on that index reflects a better fitting model. So you can see that model 6 fits the best out of all of the 2 predictor models. Model 16 fits the best out of all 3 predictor models. Model 26 fits the best out of all 4 predictor models. And then obviously model 5 only has a single model that can be fit. And I'll also mention that basically in terms of smaller is better applies to the AIC as well as to the Schwartz-Bayesian information criterion. So basically all 3 of these indexes right here, and actually this one too, smaller values reflect a better fitting model, whereas obviously the R-square value and the adjusted R-square higher values would be indicative of better model fit. The difference is that this index, and these indices right here essentially sort of account for the complexity of a model. So there's a penalty for essentially overly complex models. The same basically goes for the adjusted R-square, except again higher values on that would reflect a better fit after adjusting for model complexity and the sample size. Now, as you can see, there's a lot of information that was just given to us, both in tabular form and also in terms of graphs. And there's a lot to wade through. So another option, instead of using the all possible function, we could use the best subset function. So basically we could have OLS underscore step underscore best underscore subset, and this will essentially identify the best subset of predictors for the 1 predictor, the 2 predictor, 3 predictor, and 4 predictor, and 5 predictor models. So let's go ahead and do this. So I'm going to actually copy this and paste it in as well, and so that we can take a quick look at it. So now you can see that we have all of these indices that are given to us. So you can see for the best subsets regression right here, we've got the best model for the 1 predictor model includes just mastery goals. For the 2 predictor model, the best model contains mastery goals and interest. For the 3 predictor model, the best combination of predictors include mastery, interest, and performance goals. The best 4 predictor model includes mastery, interest, performance goals, and gender ID. And obviously there's only one 5 predictor model with all the predictors included. And so as you can see down here, if you look down below, you've got subsets regression summary. And of these, essentially model 3, which contains our 3 predictors of mastery, interest, and performance goals, is really the best representation of our data. So you can see with model 3 right here, you can see that first off, looking at the AIC, you can see its value is the lowest of all the remaining models. The SBIC is also the lowest value. The SBC right here, you can see it's almost the lowest value. It's pretty close, a close second. Then, essentially for the adjusted R-square, you can see it's a 0.3912, whereas maybe the adjusted R-square is a little bit higher for this model right here, but it also has a larger AIC and SBICs and SBCs and so forth. But overall, I would argue in favor of model 3 as containing the best subset of predictors. So that kind of concludes this walkthrough of variable selection procedures in R using the OLS RR package. So I appreciate you watching.